Hello everybody and welcome back to Decode ISC. In this video, we will be discussing logic gates. So what exactly is a logic gate? Think of them as fundamental building blocks of a digital system. At its simplest, a logic gate is an electronic circuit that makes decisions. So it takes one or more input signals, that is, here input signals are your binary inputs, that is your zeros and ones, and then it processes that to give you one exact output based on a specific logic rule. Okay? Now, there are many types of gates, but there are three very elementary gates, the most basic gates. These are AND gate, OR gate, and the NOT gate. Now, look at the AND gate. AND gates, this is the algebraic function of an AND gate, A dot B. If you look at the truth table for an AND gate, notice how only when both inputs A and B is 1 is the output also going to be 1, right? When both inputs A and B is 1 is the output going to be 1, 2. In any other circumstance, your output's going to remain 0. The second type of gate is the OR gate. The algebraic function for an OR gate is A plus B, right? And here notice how if both the input signals are 0, then the output signal becomes 0. In every other condition, it becomes 1. Output signal is 1, the exact opposite of what you watched in the AND gate. Alright? Now, the last elementary type is the NOT gate. The NOT gate is very simple. It's an inverter. And it's denoted as A bar or A dash. Okay, A bar or A dash. And essentially what it does is it inverts the input signal. So if you input 0, your output's going to be 1. And if you input 1, your output's going to be 0. Now, there are many types of gates, right? But there are two very particular ones that engineers love the most. And we call them the universal gate. Now, why do we call them the universal gate? Because you can build any other gate and or not using only NAND gates or only or NOR gates. So I can create all of these using either NAND or using NOR alone, right? And this makes manufacturing chips much easier and efficient as well. Okay, now let's look at the gates in detail. So the NAND gate is a NOT AND gate. Now what that means is it's an AND gate followed by a NOT gate, and that's how you get this symbol. Okay, how you express that is A dot B, the whole dash or the whole complement. Understand? Look at the truth table. Notice how if either inputs are 0, then the output's 1, right? If either inputs are 0, then the output's going to be 1. Now, if both inputs are 1, the output's 0. Make sense? The next one is the NOR gate. The NOR gate is a NOT OR gate. What that is it's a NOT gate followed by an it's an OR gate followed by a NOT gate. This is an AND gate followed by a NOT gate. Okay. How do you express that? A plus B, that's how you express the OR part. And then the whole complement, that's how you express the NOT OR part. Look at the truth table here. If either input is 1, the output is 0. If either input is 1, the output's going to be 0. If both inputs are 0, the output's going to be 1. Perfect. Okay, now let's check how to create the other elementary gates using only NAND gates. So it's very simple for the NOT gate. For the NOT gate, you have your input X, and then you draw a NAND gate like that. Now what happens here is you get your output's going to be X dash, right? Your output's going to be X dash, what do you get in the NAND gate. So what is the function or what happens inside is simply this. Both these inputs are X, right? So X dot X, the whole bar, right? X dot X, the whole bar is going to be X bar, and that's how you get your output. Now, let's move on to the AND part. For AND, it's very simple. It's first you have your two inputs, X and Y. You pass them. This is y, you pass them through a NAND gate, and then you pass it like that, how you did the NOT gate. So what happens here is you get x dot y, right? Now let me show you what happens here. The first operation, you get x dot y, the whole bar, and then over here what happens is x dot y, the whole complement, the whole complement. And so when you double complement it, it just becomes x dot y. So and that's how you get and. Okay, now let's focus on OR. For OR, you have your first input x, you NOT it using NAND, we already saw that above. Do the same thing for your other input y. Perfect. Now what happens here? You get this is x bar and this is y bar. Perfect. Now you pass these both through your NAND gate again. And then what happens here is x bar and y bar, the whole bar, which is equal to, using all of your Boolean law, you get what? X plus y, right? That's how you get x plus y here, and that's how you get the OR gate using NAND. Now let's go on to NOR gate. How do we get the 3 elementary gates using NOR gate only? NOT is the same logic as well. So x, your input, you pass it through a NOR gate and you get your output as x bar. Okay, next, AND is going to be the opposite of what you did in OR here. For NAND, how we used OR is how you use NOR for AND. Make sense? Let me just explain that. So what happens is you take your initial input x, you NOT it, you NOT that. Similarly, take your input y, you NOT it again, right? So over here you get x bar and y bar, and then what you do to them is you pass both of those through a NOR gate, right? And so what happens here is x bar plus y bar, the whole complement, simplifies as x and y, and here you get x and y. Now, so you might be able to guess by now how OR works. OR is simple. It's just your two inputs x passed through a NOR, which is again passed through another NOR. And what happens here? How does it work? Here it is x plus y, the whole complement, and here it becomes x plus y, the whole complement, which simplifies to x plus y, and that is how you get OR. Perfect. Finally, we have the specialty gates. The specialty gates are the XOR and XNOR gates, and the most common use is in half adder and full adder circuits that we will be discussing in the next video. In this video, we're just going to do a quick overlook on what these gates are. The XOR gate, which is the exclusive OR gate, is represented like this. It's A plus and then a circle around it, B. Now how you can also represent that is A complement B plus A B complement. This, you have to remember this. It's very, very important that you remember that expression. Now, something that you need to remember here, this is very important, remember this as well, is it outputs 1 when inputs are different. Now what that means is, if you look into the truth table, look, when inputs are different, one is 0, the other one is 1 is 1, the other is 0, the output is 1. Now if the inputs are the same, the outputs are going to be 0. Make sense? Lovely. Now let's move on to the other one, XNOR gate. XNOR gate is exclusive NOR gate. Now this is the exact opposite. How you represent it is A, then it's a AND with a circle, B, and you write it as A complement B complement plus A B. Okay, now here it is simple. It outputs 1 when inputs are same. When inputs are the same, it outputs 1, the opposite of what we learned here. So when inputs are the same, it outputs 1. And there you have it, logic gates decoded completely for your ISC prep. Keep practicing these and I will see you in the next video. Bye!